that makes this easy. So, this is Oscilloscope Basics. Thank you all for coming. My main goals tonight will be to give you a general overview of what an oscilloscope is, which you can see on the giant screen behind me, and also to show you how to use it to get useful information out of circuits, while simultaneously teaching you how not to accidentally blow it up. So, what is an oscilloscope? It is a device that measures voltage over time. So as you can see on the screen, there's a bunch of wiggly lines happening. The vertical axis is your voltage, and the horizontal axis is time. And you may be saying, well, I can measure voltage right now. I have a multimeter. Some of you who have attended my previous classes may also remember that. So, multimeters are good at measuring voltage. Right now, this is not connected to anything, so it's just giving you gibberish numbers, but I will go ahead and connect it to a pin from this circuit, and it's coming up at 4.75 volts. So you'll say, that's neat. Now, I can measure the voltage, so why do I need an oscilloscope? The reason you would need an oscilloscope is because a lot of things are not the same voltage for long enough for a multimeter to measure them accurately. So I am going to hook the multimeter up to another pin. I'm hoping I remember which one is correct. For those of you not in the space, I just have this little circuit board with a bunch of things that I programmed on it, so I'm connecting randomly to wires. Anyway, the multimeter measuring this pin, you can see here, it's switching from 0 volts to 3.3 volts and back over and over again. So that's very useful. Now, if I take the oscilloscope wire and connect it to the same pin and give it a second, I am going to press now this auto button on the oscilloscope. That's the first button that you can press. Oh, channel 2 is on. Go away, channel 2. Okay, it made everything angry. So I'm going to crank a bunch of knobs really quickly and then come back to explaining how they work later. That one. Sorry, feel free to shout questions at me as they come to you.
So, tell us about this oscilloscope.
Okay, this is a Rigol DS1202Z-E oscilloscope. It's a bunch of gibberish words. The important thing to see on there is that it's a 2-channel oscilloscope, which means I can measure 2 signals at the same time. And what is going on here?
Is it buy one, get one free?
I'm not going to put that on the internet. Huh. I seem to have made the oscilloscope angry. Thank you, demo gods.
We love you, demo gods.
Okay, I'm going to try the auto button again, because I had this working earlier. Go ahead.
Does making oscilloscopes angry happen often?
It didn't when I was preparing for the class.
It never does.
Okay.
The demo gods are the worst.
Is this not hooked up to the... No, that button is doing the thing it should be. That looks better.
Ooh. Huh.
Okay, so this is what I was trying to show you. Apparently having the multimeter hooked up to the pin at the same time as the oscilloscope caused it to do weird things. So, as you can see, you remember the multimeter was showing it switching between 0 and 3.3 volts. So now you can see the voltage is dropping and rising by a certain amount. It's kind of hard to see on the oscilloscope screen itself, but if you look down here in this corner, there is a number, it says 2.0 volts. That is the number of volts per division on the oscilloscope. So any oscilloscope you're working with will usually have a grid visible, and that grid is divided into volts per division on the vertical axis and time on the horizontal axis. And now I've bumped the camera, so hopefully it's still
It's good.
clear. Okay. If you look right here in the top corner, you can see time is noted here at 1 second per division. So when you look at this square wave, you can see that every second it's changing voltage. And if you count the squares, you can see it goes from 0 volts to, so it's 2 volts per division. That line is 2, and then it's a bit more than halfway up. So you can assume it's a 3.3 volt oscillating signal. And that's the basics of what an oscilloscope does. It's just showing you what the voltage of your circuit is doing over a time period. So I will now move on to the next pin, and this will probably look suddenly crazy. Yeah, so see how this is like a solid blob on the same time scale?
Is it just because it's talking faster?
Yeah, so you can't really tell what's happening. And let me demonstrate what happens when I connect the multimeter to it real quickly. It's saying you've got some kind of voltage that's fluctuating around 1 to 2 volts, and it doesn't really make sense.
There you go.
Yeah, so it's hard to see what is going on. The voltage seems to be dropping, going back up. The multimeter isn't giving you a very accurate picture. However, with the oscilloscope, so I'm turning a knob here that is the horizontal scaling knob. And as I turn that knob, the value for time per square increases. So now we're looking at 20 microseconds per square on the time axis, and I will reconnect the scope so you get fresh data. Give it a second there. Oh.
Oh, so you're just taking like a snapshot.
Right.
Okay.
I connected it to the wrong pin. Just a second. Okay, so there's live data again. With a digital scope, as soon as I disconnect the pin, it just saves the last time it triggered. With an analog scope, it would be gone immediately as soon as I disconnected it. So now you can see that this is an analog signal that's got the same 3.3 volts and 0 volt positions, but this one is in fact changing over time to different values. So it's just a PWM pin. I'm changing the duty cycle every, I think I got this at 5 times a second. But if you look at the time scale, we're now on 10 microseconds per square. So each cycle of this is only 40 microseconds long.
Does it tell you the frequency? Will it calculate that automatically?
This scope will calculate it automatically, but if you had an analog scope or didn't know how that worked, you can always just count the number of squares.
And then math.
So if you're at 40 microseconds per division, 1 over 4 times 10 to the negative 6th, or 40 times 10 to the negative 6th.
Why is it stretching and shrinking?
Because that's how I programmed it. I'm happy to show everybody the Rust code that this thing's running after, but yeah, in general, I just told it to increase the percentage over time.
Oh, okay.
Yeah, so so this is a situation where a multimeter is not very useful, but the oscilloscope is showing you exactly what the voltage in your circuit is doing almost immediately.
What are the little overshoot, little spiky?
Okay, well, we can zoom in and get a better look at that.
Oh.
So, any of you who have taken a physics class that went over electricity is probably familiar with the concept of a transient. And this is a very clear example of exactly what that is. So now, the scale on this is 1,000 times what it was before. So instead of 10 microseconds per division, that says, 20 nanoseconds per division.
Okay, I'm sorry. Physics was 15 years ago, and I'm not sure we went over this.
Okay, so basically, when you have a physical system and you say, move to this point, it won't actually immediately move there and stop without some effort on your part. So it will overshoot and then undershoot by a bit less, and that pattern repeats until it smooths out to where the signal is clean.
So electricity has momentum?
Basically.
Is that what capacitors are for?
Yeah, capacitor could reduce the amount of this happening. You can put assorted filters on here if you want. But, sorry, if you zoom out, I can also, so I've been leaving the voltage scaling knobs alone, so I'm only playing with the time scaling knobs for what you've been seeing so far. Above the time scaling knob, it's kind of hard to see, this says position and has left and right arrows. So you can actually move the signal over, so we can try and get a better view of the transient on the top edge. Nope, it's not. So the reason this isn't going well is because of our trigger value, which is something I wasn't quite ready to get into. So I'm going to show you a couple more signal types and then I'll go over more of what all the buttons do. Sorry, I have some notes and I'm ignoring them completely to make sure the class is as incoherent as possible.
That's the way we like it.
Okay, so that is one signal. I can also attach to this signal, which is the one I was showing at the start of class. And I'm going to make it a bit less interesting at first. So what's happening here is I am printing data to a serial pin. So those of you who are familiar with binary can probably see that this is counting up in binary from 0 to 9 before. So when I first turned it on, there were several bumps here, and then after it counted to 9 the first time, there was another set of bumps. So as you can see, it's counting up one bit at a time. So each of these, so that column there is a binary 1, or actually a 0 because this is inverted. The way serial works on this microcontroller is it's high by default and will drop low. But yeah, so the way serial data communication works is it sends data at a specific rate. So you can see this bump here is that width, and then this one is 3 wide, and the next one's 1. So you can say that's 1, 0, 0, 0, 1, 0, 0, 1, 1, and now it's 4 zeros in a row. So serial is entirely width-based, and you can just see how wide everything is to count how big it is. This is another useful situation where an oscilloscope can show you what's going on. I don't know. Any questions about data types so far?
So how crazy
That's
can the
cool.
scope get? Could you like have it extract the bit value from that?
So some digital scopes have the ability to process serial. Like one of the trigger modes I'll talk about later here is recognizing that serial data has appeared, and it will trigger when it receives the first bit of serial data. This one doesn't actually do bit analysis directly, but you can export the data over USB with this digital scope. On an analog scope, it would just be the first rising edge. It would start showing you the signal, and then as soon as it was gone, it would be done. Analog scopes, so the digital scope, it works like a microcontroller on the internals, where it's constantly taking an analog voltage signal and converting it to digital data and storing it in RAM on the machine. Whereas an analog scope was actually, through a series of amplifiers, altering the magnetic field for a cathode ray tube. And that's what would cause the beam to go up or down, is if you put 5 volts through the amplifier circuit, it will physically move the beam of electrons.
So you wouldn't be able to like get this view on this because it's just too fast. Right?
I mean, you could, because it would start at the trigger and show you everything that happens after it's triggered.
Oh.
So does that mean you'd have to like
It would need to
scroll
be
the
a
screen or something?
yeah, it would
like
need to be a cyclic pattern for an analog scope to show you this view. So if we look at the top of the scope here, you can see there's a little orange tick there. If you squint really, really hard, there's the letter T in it for trigger. So it's saying that it was triggered on this falling edge. And then it starts showing you the signal from that trigger point. Because this is a digital scope, it actually has a buffer ahead of the trigger. So there it says parameter limited. So I can scroll back that far before the trigger because it's just keeping everything in a memory buffer on the scope. With a digital scope, it would just begin showing you from the trigger on the edge of the screen every time. Sorry, analog. Right. So, I was going to show you one more signal. Many of you are familiar with the WS2812 LEDs. That is a very fast signal that looks very different from serial. And you can see here that sometimes the pulses are one size and sometimes they are twice as wide. I can squeeze it in a bit. That should make it slightly more stable. Yeah, so you can see that to send a 0 with this type of data stream, it's a skinny on pulse, and to send a 1, it's a wider on pulse. Question? Oh, sorry.
You said this was the output of an LED?
This is the control signal for WS2812 LEDs. So it's actually connected right here to this LED ring. And it's just cycling through a rainbow pattern.
So how many bits is the signal?
Each color is 24 bits. So each LED gets a red, green, and blue 8-bit signal on this particular LED.
So what is the grid time set to on this?
I believe this is updating at 5 Hertz. And then the animation pattern I'm running is just taking a Roy G. Biv rainbow and rotating it around through 16 LEDs in a circle.
So if you paused it, that would hold totally still?
Yeah, oh, so that's a good question. If you paused it, it would hold totally still. So you see this big green button you can't read right now? It says run stop. So if I hit stop, it will save the data exactly as it is, and you can actually scroll through and or overshoot immensely. But yeah, that's one of the great features about digital scopes. So you can see I was zoomed in quite a bit on here. And it's also difficult to see at the top, but there's a little bar here that shows kind of a grayed out section. That's the part of the signal it has that's not being read. And then the solid black section, black and white, shows what part of the signal you're looking at, and there's no more after that. So if I scroll over this way, you can see the grayed out section gets smaller and the whole signal appears. Another trick, I'm going back to live view, if you make the time section much smaller, or I suppose larger per division, but you make the part you're interested in smaller, you can also hit run stop on this and the whole signal is stored in RAM. So now when I zoom in, it lets you scroll through all the data all the way down the signal. And on your meter, it's almost imperceptible on the camera, but there's a thin black bar showing roughly where in the signal you are relative to the trigger.
So how big can you zoom out, like as far as your time window?
It depends on the scope. I believe this one, where does it say? I would have to look it up, but I think it has something like 24 megabytes of RAM, and it's storing a gigasample per second of data.
Wow.
So whatever fits in the scope's memory can be stored. And if you zoom out too much, it always gives you parameter limited warnings.
Can you download the data?
Yeah, so it gives you USB port options, and I believe also Ethernet on this model.
Oh, cool. So you can move it somewhere else.
So how many bits total are in that signal?
In this signal, it would be 16 times 24.
So will it calculate that for you? Can you actually
Yeah.
ask it?
How did you figure that out?
Well, I programmed it, so I know exactly what it's sending.
Oh, well.
But there,
I mean,
yeah, so there's a whole bunch of measurement and calculation tools. I will get into that after I go over what all the knobs I've been playing with while showing you the cool signals do. I figured showing you the cool things before I start talking about turn this knob to change this value would make it slightly more interesting. I don't actually know what I'm doing.
Get to the math. That's good.
So I have another question for you.
Go ahead.
So on Amazon, you can go buy these logic analyzer things.
Yep.
You plug in your computer for like $12. I assume that $12 doesn't give me as much capabilities as 10 times this. Like, what are some of the features that this can provide?
Remember,
that those logic because the logic analyzers can show me the ones and zeros of serial data. I can look at a WS2812. I can scroll back and forth with it, right?
Yep.
Bigger voltage range, right?
Yeah, you have to use software, and I'm plugging in who knows what voltage from one little dongle then into my laptop. Not sure if I want to do that.
Okay, so remember Sodar's question about the transient earlier? A logic analyzer only cares about your trigger threshold. So if it's above your trigger threshold, it will always be a binary 1. If it's below it, it will be a 0. If you had a signal that wasn't quite getting all the way up above that threshold, your logic analyzer wouldn't show you what's happening. It would just give you a bunch of zeros and ones, whether they were accurate or not. The oscilloscope, like here, if I zoom way in on this signal, you can see the full transient voltage and know what the voltage range is. Another thing that you are also bringing up is that logic analyzer pins are usually not rated higher than 5 volts. So if you have like a furnace you're trying to diagnose, those typically run on 24 volt AC logic signals. And the oscilloscope can handle that easily, whereas the logic analyzer would probably blow up.
What's the max voltage that you can put through it?
The max voltage on this, it's written right here on the face of the scope, is 300 volts RMS. One thing to be aware of, if you're going over 30 volts, the probe itself has a little switch on here, and it's currently in times 10 mode, which makes the signal larger, so it's more clear on the screen. But if you have any voltage signals higher than 30 volts, you can switch it down to times 1 mode, and then you can use it up to the rated value. So
can you show us that switch? We can't see it.
yeah, it's black on black.
Oh, okay,
so,
got
yeah,
it.
it's just a little slidey here.
Okay.
Is it smart enough to know that you're over voltaging it, or will that actually damage it if you?
It could potentially damage it. Most of them are good enough and have fuses. And there is a setting in here you have to change if you switch out of times 10 mode, or all the values it gives you will be off by a factor of 10.
What's RMS?
It's root mean square. It's a way of calculating AC voltage. If you're using a multimeter, RMS is typically the default AC voltage measurement. So it takes a bunch of fancy maths happen, and it gives you a single number that's slightly lower than peak to peak. So that's like the difference when people say 110 volts when they're talking about wall AC, that's the RMS value, and 120 volts is the peak to peak value. And they're referring to the same voltage signal. And then you had a question.
I think you already got answered. I was going to ask, like, what happens if you were to put in too much voltage? But
Yeah, ideally it will only blow a fuse. Unideally, something will melt, and we'll have to figure out what that was and repair it or replace parts.
So it is fixable, though.
Hopefully.
Hopefully.
Try not to do that. If you aren't sure, I'd rather blow up a multimeter than a scope.
You gotta be careful with solenoids too, right? Because they can put out crazy spikes.
Yeah, back EMF is a thing with any kind of inductor coil. So, if you're not sure what's going on, you can always ask other people around the hackerspace who are more familiar with electronics to get a general idea of whether or not you may blow up the scope before you connect something to it. But I'll go over some more tips on that as well. So, I'm going to turn this thing back on and return to the most boring signal. Maybe. Is it... What have I done? There we go. Nope. It was fine. Okay, so we're back to our 1 Hertz square wave signal, and I'm just going to use this as a backdrop while I talk about what the various knobs on here do. So every scope is going to have 3 main controls. The first one that I set initially and then never messed with again would be this voltage control knob. So you have a voltage knob. It's actually a per channel voltage. So I'm changing my mind, and we're going to look at a signal that updates more often. Give me just a second. Okay, so this is our PWM signal that I had shown you earlier. And the volts knob, so if you turn this knob clockwise, it will decrease the number of volts per division. So it's basically zooming in is to turn clockwise. One thing to be aware of on a digital scope is that it will show you a line at the top, but it does not necessarily mean that you're seeing the whole picture. You can see here above the volts per division, the big knob control is this one here. It says position with an up and down arrow on it. When you turn this knob clockwise, the 0 for the signal will go up. When you turn it counterclockwise, that goes down. And you can see here that as I'm lowering this, you can't actually see the top of the wave until I got it almost all the way down at the volts per division setting I'm currently on. So I'm on 500 millivolts per square. And then if you count the squares, you go 1, 2, 3, 4, 5, 6 and a half ish. So that's a 3.3 volt signal. But if I turn the knob down, now it's 1 volt per division, and you can see if I line up the bottom with the line that it's slightly over 3 volts there. So this is a knob that you will use initially when you're figuring out what kind of voltage your signal's outputting, and then probably leave alone. But the first thing you want to do when you're trying to find your signal is get the signal on the screen, and the volts per division knob is the way to do that. If you're measuring more than one signal at once, on this scope, you've got this channel 1 button there is glowing green. I will now reconnect the second probe and hit the channel 2 button. So you can see here channel 2, I'm going to put it on the same pin so you can see what's going on. Channel 2 appears in blue on this scope. So both of these are measuring the exact same signal. They're connected to the same pin physically. It's kind of hard to see there, but...
Oh, and they're just different colors based on the color that's...
So the channel 1 shows up as yellow, and the channel 2 shows up as blue on the screen.
Why are they different heights though?
Okay, so that is what I was going to say. If you look down here in the bottom corner, your channel 1's volts per division is 1 volt, but your channel 2's volts per division is 5 volts. And you can see 2 is highlighted and 1 is not. So when I turn this knob now channel 2's volts per division is 2 volts. And I can turn the position knob and move channel 2 up higher, so it's aligned with that line. So whichever one is pressed last of these 2 buttons is the one you're currently controlling with these knobs. So now I've changed them both, so now they're both set to 2 volts per division, and they look the same scale now. So you can have like a large amplified signal on one channel, and you want to compare the timing of that signal to a logic level signal. That's totally doable here by changing the volts per division per channel. But time will always be aligned on the signal. So I have a second PWM signal here, and if I connect 2 to that, you can see what the relative timing positions are on the signal here. So you'll note that the step up on both signals is always at the same time, even though it's not in the same place on the screen. They're occurring simultaneously.
That makes sense.
Yep.
I guess if you shifted the timing, it would be like total chaos.
It doesn't have to
Doesn't
be.
seem like a good.
Okay,
option
so
to have.
that is the basics of how to scale signals vertically to get them to fit on your screen.
So what if you had one signal though that had like a super wide wavelength and you wanted to like count how many times the second one corresponds with one, but if you zoom out too far then you can't see the wave.
Okay, so did I connect to the correct? I did not connect to the correct yellow one. Okay, nope.
I think so. I'm
Hold
trying to
on.
trade home, so I'm trying to get before it's too dark.
Okay, so here you go,
And
Duzzy.
see the Alex.
What I've done now is I've got channel 2 is hooked up to the 1 hertz blink signal, and channel 1 still on the PWM. So if we zoom out now,
See you next time.
quite a ways. Yeah, so now I'm at 1 second per division, and it takes the scope a second to buffer when you get to the lower time scales. So this is what you're talking about. If you wanted to count how many cycles are within a thing, in this particular case, it would be extremely frustrating to do that because you'd have to count 25,000 bumps. But you can do that by zooming out, pausing, and then scaling in to look at the two compared signals. So you can set different voltages per channel on the vertical axis, but the horizontal axis will always be time, which is absolute for both channels. Whenever it measures a sample, it measures it at the same, 10 to the minus 9th of a second as the other channel. Simultaneous measurements and data points. Okay, what is happening next? Alright, so that was your voltage control knobs. The next set of knobs are the ones that I've been using here are the time control knobs. As I mentioned, there's only one time control knob. It's channel independent, and it controls how much time per division here. By default, your trigger will always be shown as this little orange icon, and the position relative to the trigger is shown as this D value. I'm not quite sure what the D stands for, but right now I'm minus 6.2 microseconds, so it's showing the center line here is 6.2 microseconds before the trigger. If I turn the knob counterclockwise, it will slide the screen to the left, and now you can see I'm showing that center line is 40 microseconds after the trigger. So this whole time I've been talking about triggers a lot, and that is this third menu here is called the trigger menu. It says trigger there, it's kind of hard to read on the camera. But you'll see as I turn this knob, that orange line appears, and there's the little letter T on the side here. So if I slide this letter T up above where the voltage signal is, you can see it stopped updating completely because it's no longer triggering at all. If the voltage does not go past the trigger line, it doesn't trigger. Now if I slide it back down, you can see it immediately started triggering again. So your trigger line is right here. You can see the trigger line is lined up with the falling edge of this signal.
What's the purpose of that? Is that just like to avoid noise or something? Or?
Yeah, so let's look at the... What did I just connect? Okay. Nope, that's not the right one. Sorry. The LED signal is this. So I'm going to turn channel 2 off for this discussion real quick. to turn channels on or off, you just tap the two channel 1 or channel 2 buttons here by the voltage controls. Go ahead.
Apparently Cleve was asking, is there a good recommendation on a good one but that's cheap?
For purchasing a scope?
Yeah.
The Rigol 1040, I believe, is the go-to at $200. That actually gives you 4 channels at 50 megahertz. But this one here is the more current model at 200 megahertz, though only 2 channels for $300.
Does the trigger fire for both channels, or can you set it per channel?
I will get to that in just 1 second.
Okay.
So, why did my signal go away?
Is your trigger down?
Because my thing got bumped and it stopped. Okay, so what I'm going to do is zoom out and give it a second to scan. Alright, still should be triggering. Yeah. Oh, well, that's it. Okay, there we go. So, as you can see here, the data that's interesting for the LEDs is this tiny little pulse that's happening once every 200 milliseconds. So the data you're interested in, where am I? Oh, I zoomed in too much, sorry. What is normal? Okay. Is it bumped again? Sorry. Yep, I've disconnected it. There it is. Okay. So all the data, the 16 by 24-bit signal I was talking about, is sent extremely quickly, and then a bunch of nothing happens. So the useful thing is to trigger your data when something interesting happens, and then it'll show you what happens after the interesting event. And you may ask, how do I figure out what interesting event I want to look at? And that's where underneath the trigger knob that adjusts what voltage it will trigger at, there's a menu button. So if you press that menu button, that brings up options on this side of the screen here. And you can see the first trigger here, the type is edge. You can also trigger on a pulse, a slope, video. I'm not sure how that one works. I honestly haven't played with a lot of these, but it does give you many options. One thing to know, to select something from a menu, you press this intensity knob in. That one's not super intuitive. The next option you can choose is whether to trigger off channel 1, channel 2, external trigger, which would be you plug in another signal to this BNC connector on the scope here, and when that signal crosses your voltage, it will trigger. And AC. So you can trigger off, I believe, I'm not sure what AC does, honestly. Sorry. I'm a terrible teacher. The next option is slope. So when we were watching the PWM signal, I was saying it's always triggering on the downward slope. That's because I selected that. So this one would trigger when you have a bump up or down. Then you can trigger on a rising edge here or a falling edge. And whichever makes the most sense for your signal, you can just select what you want. And then it has sweep options here. Your choices are auto, normal, or single. And the exact option is also controlled by this mode button here on the thing. So if I say single, it will take the first trigger, record data, and stop. You can see it immediately turn red up top. If you put it on auto and hit run stop, it will look for changes in voltage and try to find a coherent one. The reason auto isn't working on this is because there's so much dead time, it doesn't think the once every fifth of a second is fast enough for it to be a legitimate signal. And then normal will look for the first falling edge and trigger every time it happens and show you the output on the screen. So, yep, that is trigger controls. Yeah, and if you're ever not sure what's going on, you can always try hitting the auto button, and that will, in theory, detect whatever signals are happening on both your pins and show you something useful. As you can see here, it's not always particularly helpful, because the auto function on channel 1 only picked up the noise at ground level. So your volts per division is 20 millivolts, and it's giving you a bunch of gibberish. Again, because that signal was tiny. So if you turn the volts up, wow. Am I adjusting channel 1 voltage? I'm turning the knob, but it's not changing the volts per division. There it goes. Okay, so I have now turned the volts per division on channel 1 back to 5 volts. And you can see here, there's a little yellow arrow pointing down, saying that your ground is off the bottom of the screen. So if I push the position button in, it will return your ground right to 0. And there you can now see that that big, ugly, blurry thing you saw is actually just the ground voltage amplified to a ridiculous extent, which is worthless data. And 10 millivolts is such a tiny amount, but this thing made it look like it was the whole screen. So
is that what you would adjust with the trigger?
No, so that is what I adjusted with the volts per division after hitting the auto button and getting garbage.
Right, but if you wanted to get rid of the garbage.
Right, if you wanted to get rid of the garbage, the first thing you would do is like a sanity check. What makes sense for this signal? And I'm saying 5 volts for division should show me something reasonable. So that's why I manually turned the volts per division knob and recentered the ground. And then the channel 2 signal appears to be going from 0 to off the top of the screen over and over again. So you can see that blue line across the top. That means the signal's off the top of the screen. And then this down here is again the ground being amplified. And you can see channel 2 is at 200 millivolts per division. So that's again a very small amount. So now if I push the channel 2 button and increase the voltage to, it's responding slowly. So I need to, there you go. So now channel 2's on 5 volts per division, and you can see it's not going up quite a full square over and over again.
When you push the auto button, does it try to take into account both the channels?
Yes, it will read from both channels if they are connected. So you may want to physically disconnect a channel if you don't want the auto button to try to make sense of it. Another thing to note is like the scale for these signals is once every fifth of a second you get a pulse of useful data on channel 1, and once every second the voltage changes on channel 2. That's extremely slow in the scope size, so I'm now going to move both channels back to those PWM pins. I believe this is one of them. Yeah, that's a PWM pin, and this should be. Okay, so now that I have both channels on PWM pins, these are 25 kilohertz. That's more reasonable for a scope. So I'm hitting the auto button again. And it's giving you actual useful data this time. So if you have a fast cyclic signal, the auto button is an excellent way to get very close to useful data. Whereas if you've got something that's very intermittent or spaced out, the auto button will probably show you the ground signal amplified very largely. Another thing, as far as determining what signals are useful to worry about, I am going to touch the probe with my hand and turn off channel 1. Or physically disconnect channel 1, and then hit the auto button. Oh, that didn't work. Okay. Oh, too far. Okay, so I've got the time signal is at 5 milliseconds per division. Yep, and you're seeing kind of a not quite sinusoidal wave. It's fairly pointy, but the key thing to do here is to count the number of squares. That would be 5, 10, 15, and change milliseconds per division. That is a 60 hertz wave. I am picking up ambient 60 hertz electricity running in the walls of the building. If you ever see a 60 hertz wave and you're not using an AC 60 hertz circuit, it's almost definitely not connected to what you want it to be connected to, and it's acting as an antenna picking up ambient 60 hertz signals. So just keep that in the back of your head whenever you see something that looks like this appear on your scope. You're probably just being an antenna for the wires in your walls.
Why is our AC pointy here?
I do not know. I'm a terrible antenna.
Don't be so hard on yourself.
Yeah,
We like you anyways,
that makes one of us.
but you need to improve yourself. So.
Okay, yeah.
Sure, you're gonna
If that had changed the signal, I would have been.
I mean, yeah, you can usually change the volt. Like if I touch it to this thing, the voltage goes up. That's just a random piece of metal.
Yeah, or more
Yeah.
sinusoidal, we're good.
It looks more sinusoidal. So, yeah. There you go. So that is the basics on how to control this. And now, as was requested by Dumby, let's talk about measurement.
Yeah, man.
Okay. So I'm going to go back to the auto on those PWM signals. Because I feel like, oh, well, it got the voltages right, but the timing was not the best. So this digital scope has a ton of options for measurement. There is a measure button right here. You can hit measure, and that will say the measuring source is channel 1. You can turn on a counter for channel 1, and that is giving you data here. It's 25.0013 kilohertz. I'm not sure how well that comes across on the screen.
Sure does not.
But yeah, if you turn on the counter, that's giving you a frequency measurement. That is one way to do it. I usually don't use the counter because this scope in particular has an entire measurement suite here on the left side. So again, this is going to be really hard to read on the screen. I can attempt to zoom the camera in, but I'm not sure it will be better.
Yeah, it's definitely getting better. Pretty good.
Okay, so yeah, you can see here it says period. So if I press the period button, it adds a box down here at the bottom of the screen, and it says your period is 40.00 microseconds. If I press the frequency button, there is also a frequency 25.0 kilohertz down at the bottom of the screen. So Sodar, you brought up the rise time where it kind of spikes and then wiggles. It measures that for you. If I hit the rise time button, it will show rise. And it's saying it's less than 200 nanoseconds, which is as small as it can measure for that value. You can measure the width of your pulses. This one will be changing as it goes. What I mentioned before, when I hit the measure button, it says source is channel 1. It is only measuring on channel 1, and you can tell that because all of these values are yellow. If I were to change this to channel 2, and then hit, what was it, width, it will add a blue button that measures the width of the blue one. So you can see this one starts out around 40 and drops, and this one starts out near 0 and grows towards 40. As the blue signal gets wider, the yellow signal gets skinnier. But yeah, it's important to know you can hit the measure button over on the side here and change the source using these buttons while you're measuring. And then you've got, so that's the width of the on pulse. You can also measure the width of the off pulse. And you'll note when I pressed that button, it pushed the first one I did, which was frequency, off the edge. So you can only have 5 of these measurements active on the screen at once, unless you hit the measure all button here, which will eat a bunch of your screen, but show you an absurd amount of information about your signals. I don't know if that's legible.
It's legible enough.
Okay. So, one thing to note, if you look on the side here, there are 4 little dots next to the icons. If you hit the down arrow, it will give you even further measuring options. Yeah, you can get the rate at which things go up or down. You can get the delay between signal 1 and signal 2. So like if signal 1 rises and then signal 2 rises after it in a repeating pattern, you can use those delay measurements. Yeah, so the delay between 1 and 2 is 100 nanoseconds, and it stays that way as long as they're both on.
Is that signal 1 or signal 2?
Yeah, so it's the rise. This is measuring the delay between signal 1 rising to the next time signal 2 rises. And then you can also do phase measurements for AC voltages. If none of this is good enough for you, I'm going to zoom back out. There is this cursor button. So you can press cursor here. Oh, actually, I'm going to go back to measure and turn off measure all. Okay, so I've hit cursor, and it says cursor mode off on the menu. If I press this button and say, give me manual cursors, you may now use the intensity knob to move this manual cursor on screen. If you push it again, you can move the second cursor, and then it gives you information about the difference or distance between those cursors. If you want to use vertical cursors instead of horizontal, you hit this select button, and then you can move cursor 1 and cursor 2, again by pressing the intensity button. The intensity button kind of doubles as your selector knob whenever it's not being used for intensity. And then the source on this doesn't particularly matter for manual cursor measurement, but if you're using other cursor modes like track, it will attempt to align with parts of the signal when you turn the knob. So you can see like these little white blurry things that are probably really hard to see on the camera are jumping up and down with the signal, and they'll snap to corners, edges, whatever they can find, basically. So there's a lot of options in manual cursor mode. Yeah, so that's cursors. You can hit the cursor button over here to turn them off, as well as turn them back on. That cycles through the modes. Okay, what else have I got here? Right, how not to accidentally blow this up. So, one thing you should be aware of is the physical scope probes here that are connected via these BNC connectors. They have an outer shielding ring and the inner signal ring. That shielding is connected to the shielding on this connector, and you can see there's a little golden signal pin on the inside. The importantest thing to note is that these outer shielding rings are connected through the internal scopes directly to your earth mains ground. That's the third pin on your outlets. Let's drag one over here. So your standard American AC outlets, they have a hot pin, a neutral pin, and this third round ground pin. That ground pin is connected, hopefully, at your electrical panel to physical earth ground and tied to the neutral pin electrically. So anything you hook up to this scope is going to need to either be floating, like a battery-operated device like a phone, or when you connect your scope probe, which looks like this, you've got two parts on here. One is this ground clip, which needs to be connected to a ground pin. So for instance, all the circuits I've been using today are connected to the earth mains ground through my laptop's USB connection. My laptop's plugged in to earth mains, so that signal would travel all the way through here, straight to this pin. And if you connect this pin to, say, the 5-volt signal on here, it's the same as shorting 5 volts straight to earth mains ground, which will begin melting things. So if you're ever not sure, you can go back to your trusty multimeter in resistance measurement mode and check the voltage between the ground. So you can connect it right to the ground pin on your scope probe. This is me connecting my multimeter to the ground pin. And then if I measure, say, the resistance to the USB plug on my laptop, my multimeter, oh, come back here. Sorry. This is happening off camera for those in the Discord. I've connected to the ground pin on the scope and my laptop multimeter, and it's showing up at, almost 1 kiloohm. So, oh, sorry. 0.96 kiloohms. So this is actually, my laptop apparently has some protection against stupid people like me doing exactly what I'm doing.
Yay.
But yeah, if you're ever not sure, just get out your connectivity meter or ohm meter and make sure the ground on whatever circuit you're measuring is a very low resistance relative to whatever you're connecting the scope to. So I will connect the multimeter. Yeah, there you go. So we're at less than 60 ohms going from the multimeter probe ground to the circuit ground. That's a very low number to have shorted to earth mains. So you would not want to connect things to not ground on this circuit because it's fed through something that's also connected to earth mains. So just something to keep in mind. If you're ever not sure, again, you can find someone at the hackerspace who will probably be able to tell you if you're about to blow something up or not. Yeah, that was the safety warning I wanted to end on. So I'll open it up to any other questions you guys have about basic operations.
So, kind of back to the safety thing, let's say you actually are going to be measuring something with like an inductor in there. Is there a way that you can actually protect this from like transient spikes that you don't expect? Like,
there should be fuses in here. I have not actually opened this one up to find and verify their size, but I mean, if you're, I wouldn't, why would you need to like hook up a scope to the voltage on a motor is my first thought.
I'm thinking more along the lines of like, let's say if you have open up a power supply and you have some inductors in there and it's maybe switching, I could see you getting a really high transient spike off of that. I'm wondering if is there like a time factor in the transient spike that you have to worry about?
Yeah, I mean, that's true about just about anything. So if it's an extremely short transient spike, it's not going to have the high voltage for long enough to overheat the components and start melting them. But if it's doing that repeatedly, like in a switching mode power supply, then you may not want to connect this directly to it. A lot of multimeters will be rated for higher voltages than the scope is, so you may be able to hook them up to the AC setting and measure that to see if there's any large pulses you should be worried about.
So a minute ago, you connected the ground of the oscilloscope to the ground of your laptop?
No, I was measuring the resistance between the ground on the oscilloscope and the ground on my laptop.
Okay.
And that was just so I could see if there's essentially a short between the two, so I would know that I cannot connect the ground pin on the scope probe to the non-ground pins on a circuit connected to my laptop.
Okay.
Essentially, if you have a very low resistance between the grounds, that means they're effectively shorted together. So you would not want to connect this pin, which is shorted to ground, to any other voltage pins. Like, I would not want to connect this ground pin to the logic pins that I've been measuring all night on my circuit, because those would essentially be shorting 3.3 volts to ground through whatever that small resistance value was.
You have to complete the circuit by hooking up the probe end to...
No, so essentially as soon as you connect this ground clip, it travels through the ground clip. This is actually just a little clippy thing on the outside. You can see the shiny metal in there a bit. It goes straight down the shielding of the wire to the earth-grounded metal parts of the scope. So if you connected this right to 3.3 volts, it would be taking 3.3 volts and shooting it straight into earth main through the scope. And the scope is going to melt before your 12-gauge ground wire in your wall outlet does.
Okay. But if you were just hooking this up to some battery-powered device, that wouldn't...
Yeah, so if I were to measure the resistance between the ground pin on this and, say, anything connected to my phone, like a speaker wire, the phone is completely floating, so it would have a very large resistance because there's no circuit for the electrons to travel through.
Okay, so randomly, how do phones get to charge then? 'Cause when you hook
Well,
them up-
when you plug the phone into charge, then it's connected through your charger to the wall outlet. And some of those chargers may just be a transformer that's floating.
Okay.
So it may not actually be connected to earth ground. Most phone chargers are just the two pins, so there's no direct path from earth ground to the thing. It would be running current through neutral through the transformer, which is usually a high enough resistance, you're probably fine.
And it's worth noting here too that some phone chargers actually have the ground pin floating at near mains voltage, and that can get kind of hairy really quick. So
Yeah, if you have anything that plugs in with a 3-prong plug, it's safe to assume that ground for whatever's plugged in with the 3-prong plug is the same ground that the oscilloscope's using. If it's a 2-prong plug, it could go either way depending on how they built the thing, and don't make any assumptions. You can verify again by measuring the resistance between ground on one device and ground on the other, and if it's a large value, then it's probably not connected directly to earth ground main.
What would you say is the most common like application of something like it?
So say you walked up and you saw this thing sitting on a desk and you're like, what is it doing? You can start hooking the oscilloscope up to the pins and seeing what each pin signal is outputting and try to determine what the device is doing.
Do you have an example of like something that we could troubleshoot? Like not necessarily troubleshoot, but like something like that.
Yeah,
Like,
does anybody have a random electronic gadget they want to see what signals it's outputting?
Sure.
Yeah.
What does the math button do, by the way?
Oh, the math button. Did I skip the math button? I'm sorry. The math button will do math on your two signals. So let me...
Do like the Fourier transform and stuff?
Yes, actually. This does have a Fourier transform button.
So cool.
Okay, so I'm going to go back to our this signal. So that's the one that goes from 0 to 3,3, and then this one's the PWM signal. So now when I hit the math button, it brings up this menu here. So I'm saying operator A plus B, and then I turn the operation on. You get this purple line that's showing A plus B. Then here you see source A is channel 1, and source B is also channel 1. So that's not particularly useful. If we change source B to channel 2, now you can see it is going off the top of the screen. But that, oh, I overshot, sorry. Source B is channel 2, okay. There you go. Now you can see that source B is moving up relative to its ground point by the voltage of source A.
What are the other operators under A plus B?
Yeah, so you can do A plus B, A minus B, A times B, A divided by B, fast Fourier transform. That one will show you frequency domain. So let's do frequency domain on, no, we want channel 2 because that's the one that actually has a repeating signal. Oh, come on. Okay, so it's saying there's a large spike around, let's see. So this is really hard to read, 500 kilohertz per horizontal division. And we've got a large spike around 5, 10, 15, 20, 25 kilohertz, and then it trails off. So you can assume there's a 25 kilohertz component to the 25 kilohertz PWM signal.
Sodar, do you have any of your cool gadgets that you brought?
I didn't bring anything.
Okay.
I just wanted to focus on the class.
Okay.
Because I could give you this.
All right. Programmer?
Yeah.
I would have to program something.
Oh, that's a problem.
Yeah. Let's see.
It's kind of just something like in one of the
Well, honestly, I think that these are a good enough example. If we just walk through as an example, like
Of how. Yeah.
Yeah, just talk us through, you know, your analysis of the signal that's either
Okay.
for the signal.
So I'm going to completely disconnect channel 2 now, and let's turn math off by pressing the math button.
And as part of it, will you like walk through, let's say you have a pin on this microcontroller, you're trying to figure out what it does, right? How do I not blow up my oscilloscope
Okay.
while figuring it out, right?
Yeah,
so
so
it's
like
just
an end example.
exactly. So we have this pin sitting here, pin 2 on the microcontroller. Now what? How do we make sure we don't blow it up? What do we check first? Do we need to put a multimeter on it first? Do we need to
Okay.
do this?
Yeah, I can definitely walk through all of that, and probably should have put it in my class to begin with. Thank you.
Because, like, the thing is all the time I get a piece of electronics, and I'm like, okay, well, I want to just start touching everything, but I also don't want to blow anything up.
Okay, so I'm turning off channel 2.
What is this debug pin do? Does this give me 12 volts? Does it give me 1,000 volts? Is it just serial output? I don't know.
One thing I forgot to mention, the intensity knob does control the intensity of the signal. So if I turn this all the way down, you can see it got a little fadey. And if you turn it all the way up, it gets very dark.
The other question I have is, can we do this in line as well? Or do we have to,
like current measurement?
Yeah, say you've got a microcontroller talking to another microcontroller. Can I just touch the line in between and not mess up the communications between the two?
So essentially what's happening inside of here is your signal has a 1 mega ohm resistor between it and the ground. So as long as putting a 1 mega ohm resistor into that circuit would not damage it, it will be fine.
And usually it won't.
For like line level logic stuff, I would not worry about it at all. It's just going to measure the voltage.
That's what you're doing with the LEDs is in line.
Yeah, you just measure the voltage relative to ground. Like the LEDs have been running this whole class whether I'm connected to them or not, because that signal going through a 1 mega ohm resistor does not have any effect on the voltage on the other end.
When would that be a problem?
Like radio equipment?
When would that be a problem?
Yeah, if you've got some... Yeah, I can't... There's almost nothing at logic level for microcontroller stuff that I can think of where a mega ohm resistor anywhere near it is going to matter. higher resistance than air.
So this is set up for like triggering on stuff. Can you do cheesy stuff like just plug it into a audio outline and just view the raw waveform?
Probably. I tried to get that demo working earlier, and I think my phone knows it's not actually connected to anything, so it wasn't outputting. But we can come back to that. I want to go through the example they had requested. So let's say you wander into a room and you see a tangled mess of things that looks like this and has an LED ring on it. And you say, I want to know how that works. You notice there are 3 pins going to the LED ring, and it's connected via USB. So the first thing to check would be whether or not you're going to blow it up by connecting the ground pin to anything. To do that, you get out your multimeter and turn it on to ohm measurement mode. And you can see here it's not touching anything and it says 0 load. So
what's the ohm measurement mode? I can't really see the symbol.
Oh, it's an omega sign.
Okay.
And on this scope, it's also the same as connectivity testing. If I hit the select button, it will beep instead of measuring the ohms if it's a low value.
Okay.
But if it's on select mode, it will actually tell you the actual value of the ohms. So I'm going to lean this here. Hopefully it stays legible. I'm now going to take the one clip and connect it directly to ground on the scope. I'm doing that by touching the casing here. You could alternatively connect it to the ground pin on your probe.
What about the little end thing? Is that also ground?
The little and thing? Which?
Or like
the far right.
Oh, right here?
Is that?
So one of these is ground.
Or is that for calibration?
Yeah, one of these is ground. You can see here there's kind of a little earth symbol. It's a line straight down with 3 forks pointed down at an angle. So I can connect it to this one, that is the ground signal. This one here is a bumpy signal. That's your calibration signal. It goes, I think, 1.3 volts.
Okay.
You would not want to connect it to that for this test. So you've connected one pin there, and then you take the other probe from your multimeter and you connect it to ground on the microcontroller. I know this is ground on the microcontroller because it says G on the pin I'm connected to. You probably can't see that on the camera, but you can read it. If you're not sure, you can try, like, the outside of a USB connector is almost always going to be ground. And if it isn't, then you probably have one of those devices designed to harm your computer. So you could connect to that. What you see here is that it's a low value. It's like 200 ohms on the USB connector. If I go straight to the ground pin, yeah, still 200 ohms. So if you're less than, say, 1,000 ohms, it's fairly safe to assume that you're connected to earth mains ground. So that just means that when you connect your... Oh, I disconnected my USB on the computer side, sorry. Yeah, when you connect your probe, you will always want this clip for the scope to be connected to ground on the circuit. That's all that step meant. So I will now connect one side of the probe on the scope to the circuit. I also realize I didn't go over how the scope probes work. You've got this big kind of plastic thing. If you pull down on the connector, you'll see this little hook pop out. And if you wrap the hook around the thing and let go, it will latch on to whatever wire you want to check. So you've got your LED ring. I'm going to remove the multimeter from the area because it's in the way. This will be easier to do backwards after I've dragged all the cords across it. Right, so you've got this circuit and there are 3 wires running from the microcontroller to the LED ring. You're not sure which wire is which. You can look at the board and try to figure it out, but at this point you know that the ground is connected to ground on the microcontroller, so you should be safe to connect the probe to any of the 3 wires, whether they're ground or signal voltage, and it will show you on the scope what's what. So I'm going to connect to the first wire and see what happens. you'll note that nothing at all has changed. And that's because I connected it to the ground wire. So, wasn't that one. You can now move on to the second of the 3 wires. When I connected it to the second wire, you can see it immediately jumped up. But I did some prep work before I started connecting it. So you can see on the scope, your ground is this little yellow tab on the side. And I've got that on the screen where it's clearly visible, so I knew that the ground signal was somewhere. I also preset the voltage to 2 volts per division, so that when the signal jumped, it would be a reasonable amount and you could see it on there. I also preset the trigger to be slightly higher than ground, so if it went up, it would refresh the scope. If it doesn't go over your trigger value, the screen will just stay wherever it was, and you can connect it to 100 things, but if your trigger's set at 23 volts and all your signals are at 5, it's never going to turn on. So you can prime the pump like that. You could also try the auto button, but as we saw earlier on this exact circuit, it doesn't always work, so it's good to just use some mental rule of thumbs. It's a microcontroller, so having 5 to 10 volts visible on the screen is usually the right range.
So is that almost like 5 volts?
Yes,
So
so
how do you
this is
tell-
actually 5 volt power.
How do you tell if it's 5 volts or it's 3.3?
So you can see the ground symbol here, and then you count up 1, 2, and change, so it's just under 5 volts.
You
Alternatively,
said 1, 2, and change. That
yeah,
sounds
so
like 2.5.
it's not quite a half, it's actually slightly lower.
Oh, that's because each square is 2
Each
volts.
square is 2 volts,
Got it.
as
Okay,
noted
2,
in the bottom
4.
right.
Yeah.
Yeah, another thing, if you go up here to the measurement, you can, that's one. See here how it says horizontal, and I went through all 4 tabs?
Okay.
If you push the menu button, it will switch to vertical, and then you can hit this Vmax button, and it will show you there the maximum voltage is 4.8 volts. So, again, the measuring functions of the digital oscilloscope are very handy, but you can always count boxes if you need to.
So
Okay.
it sounds like this pin is
This pin is the constant 5 volt power. There's no sign of a signal. So
not quite perfect 5 volt.
yeah, it's whatever the USB on my laptop is. So good work, Dell. Okay, so now I have connected to the 3rd pin. And one thing you'll note is it looks like a ground pin, but if you keep watching, you occasionally see things happening. So the trigger mode is currently set to auto, but because the signal is not repeating fast enough for the scope to think it's a good signal, it's not giving you any useful data. If you change the trigger mode to normal, it should catch a data. You may need to wiggle the trigger. Nope. Okay, sometimes if it doesn't trigger, you may need to reduce the time per square or jiggle your connections.
Jiggling.
I mean, you all saw this working before, right?
Mm-hmm.
Oh, that's not where I want to trigger. Yeah.
But didn't that trigger lever just say 7 volts?
Did it? Oh,
Trigger.
yeah.
So why is it?
Okay, so something is clearly wrong here. If I hit the menu button on the trigger, it's trying to trigger off channel 2.
Nothing's plugged into channel 2.
Right, so thank you for pointing out the trigger voltage. That could have taken longer. So now that it's triggering on the proper channel, you can see that it has found a signal that is the WS2812 LEDs.
And so, like, what would be your thought process about?
So my thought process is, first, it's having a seizure, so I'm going to shuffle it to one side. It usually stabilizes, but not always. There we go. You may just need to zoom in more until it finds a clean edge. But you can see that the signal consists of pulses that are changing in width, so it's probably something like a remote controls IR sensor or these LEDs, which I am extremely familiar with and just recognize from that. If you don't know, you can probably take a picture of the scope and do a reverse image search and see what comes up. I have found out things by doing that. It doesn't always work, but if you just get the zoomed in part, sometimes you find an article that gives you a vocabulary word to start Googling.
So it would be useful at this point to maybe switch over to a logic analyzer to see what's actually in that signal?
Yeah, so if you have access to a logic analyzer, when dealing with this kind of signal, that would definitely be something I would go to. But if you don't, the first thing I want to know is how long is this whole signal?
Right.
So I would zoom out and see it's just a small pulse that's happening somewhat irregularly. And that pulse is... where are we at? So if you look at your so the controller tries to be helpful. If you keep turning to slide sideways, it will speed up exponentially. So just something to be aware of if you're trying to slide the signal sideways. It also likes to snap to the 0 point. But you're at 100 microseconds per division, so this is just under 500 microseconds worth of pulses. And then if you zoom in, you can see that each pulse is very consistently something. I don't feel like actually measuring that, so I'm going to go to the menu and have it tell me the frequency. And the frequency on this is 847 kilohertz. So if you Google that and it doesn't tell you anything, you can also measure the period and say what signal runs at 1.18 microseconds. Or probably say like 1200 nanoseconds, 1.2 microseconds. I believe the code's actually written for 1200 nanoseconds, and that's snapping to the closest clock cycle.
Okay, so from this you can determine you're on a data line because it's actually
it's
variable information.
It's a data line that's sending a pulse of data every so often to the LED peripheral. So you can assume that this data somehow corresponds to the values of those LEDs. And you can kind of see binary counting where it's alternating back and forth. I may not be able to zoom to a level that would be clear. Another feature of the scope is you can hit the single button and then it will just take a sample. So you can zoom in and actually analyze just a single sample.
A snapshot.
1, 2, 3, 4. You can count how many pulses there are.
And is there a function of where it'll just calculate that for us?
Possibly. I have not dug into all the fancy maths on here because I do own a logic analyzer and generally prefer using it for this type of thing.
Right.
But
so really the best application would just be to get a general idea of the shape and form of the signal and not to do any signal analysis or decoding.
I'm going to go through here and say, hey, there you go, count pulses. 379 pulses.
Okay.
That's cool.
And so that correlates with what you said, 24 bits per LED, and there's however many LEDs.
Yeah, 16. And that's assuming my code's written well enough that I'm not sending more than there are LEDs. 379 doesn't sound like it's divisible by the numbers it should be.
38, it's over 30.
To the calculator.
Over 9,000.
Okay, 379 over 16 is 23.6875 per LED. So it's probably an off by 1 and there's 24 per LED. I'm betting it doesn't count the initial pulse because it's measuring from wherever it triggered and not the whole.
So then without knowing much about the protocol behind WS2812, we can see, okay, so it's sending a signal of however many per...
Of 24 per 16.
So that helps us give us some hints to start reversing.
Yeah, and then you can say it's RGB because you've got 8, 8, and 8.
Utilizing this, can you get the counter to say this has gone up and down X times, like in this snapshot?
Probably. I'm not entirely sure when you use the automatic features. I think it makes some assumptions, and I'm not exactly sure what the assumptions are. It could be starting at the trigger and going to the end of what it measured. It could be reading what's currently on the screen. I guess an easy way to check that. Okay, so it is reading what's currently on the screen. Because if I zoom in here, it says there's 5 pulses, and if I zoom out there, it says there's 10 pulses.
Oh, sweet.
So there's 50, 100, and when I get all the way out, oh, see, and if the resolution gets too low, it can't calculate the pulses because it dropped to 204 when I zoomed out too much. I believe there is a fine, so you know how you can push the buttons? If you push the position knob, it will center. No, there was one of these. It may be if you push the position knob, no. Something, I forget, there was a way, maybe push this. No, that shows you the portion of the total signal you're looking at when you push the time button. Somewhere in here, I've forgotten exactly where, there's a way to do fine adjustments on the zoom and voltage scaling per division. But I don't remember where that is. Oh, another awesome thing. There is a help button over here on the scope. If you push the help button and then press literally any button on here, it gives you a help message that tells you what it does. So that's probably completely illegible, but yeah, press this key to turn the delayed scan on and off. The delayed, yeah, so that was the zoom in thing that I just found. If I turn the knob, it doesn't seem to work. Yeah, if I hit the menu button, horizontal control menu, there may be a way in the menu to change. Nope, that's just delayed on or off. Oh, another fun thing, unrelated to our reverse engineering problem, if I go back to the 1 Hertz signal, you can hit this time base and change it to XY mode. When you see all those videos on the internet, it will plot your channel 1 probe as your vertical axis and your channel 2 probe as your horizontal axis. That's how you get people playing Quake on oscilloscopes and seeing all the cool audio visualizations. And then the other mode down here is called roll mode. So if you have a slow signal and you turn it on to roll mode, it will just continuously scroll off the side of the screen while showing you that signal. Yeah, you're definitely much more limited on how much you can zoom in roll mode though. The smallest time per division you can get down to is 100 milliseconds.
So I remember you were talking about the logic analyzer. I remember this, and I just double checked to look it up. You can plug, my understanding is you can plug this into your computer, because there's a USB jack and an Ethernet. You can either use the Ethernet, but you probably won't set that up here, right? But use the USB, and you can use the logic analyzer on your laptop. With this as the actual analyzer. So you can use Pulse View and just connect directly to the Rigel. I haven't tried it yet, but it seems pretty interesting.
There is an acquire button here, and when you push it, it brings up the menu, and you can tell it, or no, it's not acquire, it's storage, I think. And it has assorted modes of how you can store things and export them and save them. I have not looked into the computer-aided features of this scope very much yet.
That seems pretty interesting.
I mean, before I had this, I was running the analog scopes, which, I mean, now that we've looked at the scope I brought in enough, I'm gonna turn the camera, or maybe.
Good luck. Turn the camera, just turn it.
Okay. Yeah, I'll give it my best shot and show everybody my old analog scope that's cathode ray tube has died just before this class. Well, sometime in the last couple of years. So, on the old analog scope, you'll see it has a bunch of the same controls. Is this bar in the way?
Not much.
It's good.
It's in my way.
That's what matters.
Now, is this a transistor OG?
No, I had this 5 years before I even met Decaf.
Oh.
I bought this in, what, 2003? 4? Somewhere around there. And it was probably built sometime in the early 80s. Anyway, you'll see there's a bunch of the exact same controls we had before. There are vertical position knobs. There are actually 2 of them on this because we don't have a channel selector button. And then physical switches to control the volts per division. Probably really hard to see on the camera, but if you look in there, you can see there's actual numbers there. 2 of them are highlighted. You've got, let's see, that's 2 and 0.2 volts per division, and that's for the times 10 or not on the probe. You don't actually get any kind of software telling you what the voltages are on this. You literally have to count squares, which is why I'm so familiar with that and default to it. You also have on the other side the time division knob. And again, it's just a physical selector that changes the components in the amplifier circuit that's moving the actual cathode ray. So as you crank this all the way up, it would scan faster side to side across the screen. And then if you turned it all the way down, you would have one very bright dot moving very slowly across the screen. There's knobs for physically controlling intensity. You also had a beam find button, so if you had it set to something and your signal was off the top of the screen, you don't get the handy line like you do on the actual scopes. It's just literally not shining in the phosphoring piece of glass, so you don't know where your beam is. But if you hit the beam find, it physically moves a lens in front of the cathode ray tube and zooms the whole signal down so you can find where the beam is and know how to adjust it. But I mean, aside from being really cool and having extremely satisfying switches and knobs on here, the digital scope's better in every way at this point. So
does this one have the trigger thing too?
Yeah, it has a whole set of trigger options, and you've got like these knobs here. You can adjust the level with a it's kind of hard to see on the camera, but there's a line on the pot. It's right at the top now to change the voltage it will trigger at relative to 0. And then there's a switch here on the end of the knob that switches from rising edge to falling edge. And it does have an external trigger option as well. And it has 2 different triggers, and you can have delayed triggering. When A goes up and then B goes down, it would trigger. There's a lot of settings here in the physical setup. So there's A trigger setting and B trigger setting, and they both have these levers to change which channel they're on, types of triggering, types of AC-DC coupling. A lot of things you don't need to worry about with the digital scope unless, again, you forget to go to the menu and change it to the correct channel. So, any other questions about the scope? Sodar.
I'm wondering, do you have to calibrate is the calibration part?
So, when I first bought the scope, there's a calibration procedure for it, and you connect, I guess I should point the camera back at the scope I'm talking about. You're all on the internet now too. Okay, anyway, those pins I mentioned earlier, you connect the ground pin to here, and the, come on, doesn't want to clip, there it goes, and the probe pin to here, and this one you can definitely hit auto on.
Okay.
So you can see there what it looks like. When I first got the scope, it was actually... Here, does anybody have a tiny screwdriver? Maybe I do.
If you don't, I'm disappointed in you.
Yeah. Well, My old Leatherman did.
I got a small Phillips.
So you actually have to like.
I have a small
Yeah,
screwdriver.
there's a
in a pot.
screw inside the probe, and I'm gonna mess
right.
with it.
Okay.
Alright, hang on. Oh.
If I can find the side of it it's on.
And you basically zero it out or something.
Yeah. So if you look in the camera here, it's really hard to see, but there's that little dot by my finger is a screw hole. And you adjust it, so that adjusts the capacitance of the probe to match the capacitance of the scope. And when I turn it, the transients on the ends of these are going to go way out of whack. So as long as your calibration signal that the probe's generating looks square.
So the calibration is just.
Yeah, you calibrate the probe to match the capacitance of your scope when you get it, and it's in the instructions. Wait, I have like 2 of those in this bag right here. Sorry.
I'm disappointed if you don't have
Yeah,
them.
no, I do have them. I just froze because, you know.
Because hackerspace.
Yeah.
Everyone's looking at you.
Demo gods.
No, this one's just personal failings. Probably too small, but yeah, definitely too small. It was spinning inside the slot. Gotta sort your screwdrivers better.
Yeah.
I thought it was perfectly sorted.
It is. I just don't know this kit. Yeah, so there you can see if it's turned down too far, the corners drop out, and if you go up, the corners go too high.
So you can get
What are you turning?
There's a little screw inside the probe itself that adjusts the capacitance of the probes.
So on mine, it's right here.
So you can have multiple tune for different applications.
Yeah, well, it's usually per scope.
Okay.
So you tune your probe to your scope and then not use it on other things.
Makes sense. Because there's little variations in each scope.
Yeah, it's
Is there
just like you buy a capacitor and they're plus or minus N%. So rather than spend $100 on a super precise capacitor, you add a variable to the system that you can adjust.
Yeah, that makes a lot of sense.
So I think I may have misunderstood when you talked about it before, but you were saying there were different types of triggers.
Yeah, so if we go to the trigger menu, you can trigger off an edge, which is just when the voltage goes up or down past a threshold, it will trigger. You can trigger on a pulse, which is looking for, like, is it a wide pulse? Is it a skinny pulse?
Oh, gotcha.
You can trigger on slope.
I definitely need one of those in my backpack always.
Just like it's way better form factor than the ones that are just like.
Yeah, so there's not much slope in our calibration signal.
It's just heavy.
What's the one? I thought that there was one that you guys were using
Huh.
as motor.
So that looks like, yeah, when it's sloping upward, it will trigger. So I guess it thought there was enough down or up slope there. Yeah, I guess only some of these apply to this signal. You can trigger on pattern.
There was another one. I don't know if it's Tim's or
High, low, or X. Oh, yeah. So if it's high, it will trigger. If it is low, yeah. So see, when you're on high, it triggers at the end of the high. When you're on low, it triggers at the end of the low. When you're on rising edge, it triggers on a rising edge.
What's the point in triggering it at the high or the low or whatever?
Just so it snaps to the part you care about. Like on the serial signal, it's high for a very long time, and then it sends data, and then it goes back to being high for a very long time. So if you triggered at the end of that long high, you would get right the start of your serial data.
Okay. Oh, that makes sense.
Yeah, and you can do durations.
sample and hold?
All bits. Yeah, I have not messed with a lot of these, so I'm kind of winging it.
Is it trigger? That seems weird.
You should have a slide that indicates your window.
I don't know what runt is. Maybe just a tiny pulse of a certain value. You can look for a window with things happening in it.
So I2C and what was it? So
Serial.
It would trigger like when the technical I2C trigger.
Yeah, or you could hook it up like if you have an SPI signal that uses a control pin.
Okay.
You can trigger when that control pin drops, and then it will just read the data that you care about for the device you're looking at.
That's handy.
Yeah, I'm not sure. Yeah, like window. That's... Yeah, these get very complicated, and I haven't used many of them. I mean, I guess I do have serial here of this polarity, so let's see if it triggers when I connect it to my circuit on my serial pin. It doesn't. Oh, because my baud rate is set absurdly low. Megabaud. Nope. I don't know what baud rate this is actually at. It's probably something like 2 megabaud because the default is not to limit it anymore on microcontrollers unless I go out of my way to make it slower. But in theory, if I had a serial device of a known baud rate, I should be able to trigger when it detects that it's sending valid data on this pin.
What's under the start again? Is that
under start?
Like, yeah. Oh, you can start it on an error? That's cool.
Yeah, or check error.
That's where I would start.
Data 8. So it won't do it until you get 8 bits on the pin. Because serial's a well-defined protocol, and if anything, there's a parity bit on every byte. So if that parity bit doesn't match,
that's so cool.
It would give you that. When data 8 bits. Yeah. Huh. User. So you can in theory adjust this, but yeah, again, I haven't spent a lot of time with these because I have a logic analyzer that I prefer to use when I know it's a logic level signal.
Oh, right. There's one question from Discord that hasn't been asked.
Oops.
If the device is being powered through a GFCI circuit breaker, is there a risk of tripping the breaker if you are using it properly, or if you hook the ground clip in a way that shorts something to earth main ground?
You would probably trip the breaker if you connected the ground clip to something you shouldn't when it's plugged into a GFCI outlet.
Okay.
Assuming the outlet is working correctly, that's exactly the kind of thing that it's designed to be tripped for. So that could be a good way to protect the scope, actually, is make sure it's plugged into a GFCI outlet.
Hey, ours is.
Yeah. That's good.
You want to test it?
Not really.
Yeah, I didn't think so. Me neither.
If you bet me $300, it won't break.
Oh,
and I can buy a replacement if it does.
Cool. Any more questions before we let Tim go?
Okay, well, thanks
hang on,
for...
we got someone typing.
Oh.
Nope, not important. Okay, everyone, thank you, Tim.
All right, thanks.